Hello, everyone. Welcome. And welcome to our live stream audience. Before we get started on our main presentation, we're going to have a poster presentation by Farah Alshanik. Farah is a PhD student at Clemson, and she just completed an internship with HPCC Systems and has a very interesting poster there. Farah?
Hello, everyone. As Roger mentioned, I am Farah Alshanik, PhD student in Clemson University, and I'm working with Dr. Amy Abon in DICE Lab, Data Intensive Computing Ecosystem Lab. My project is a summary of, or this poster is a summary of internship project last summer. I've worked on this project with Kevin and Roger and my advisor, Dr. Abon. So this project include the equivalence term to the text search bundle. First, the text search bundle is an open source project from LexisNexis, but this project is a full text search. So when the user uses some search query, it only returns the set of documents that match exactly the keywords in the search query. So in order to improve the performance, we decided to include the equivalence terms to this project. And we use two methods. One, we use the MOBI thesaurus, which is an open source dataset that contains around 30,000 root words with 2.5 million synonyms. And we link this dataset to the text search bundle. This is the dataset, but it's not appear. So, yeah, there's a problem. So it's not clear enough. So, okay. So, as I said, this is the MOBI thesaurus. It's an open source dataset that you can use to find the set of the synonyms of any word. And after that, so the user can enter any search query. Then we solve the initialism and the abbreviation problem. These problems exist in the text search. The initialism, when we have a word or a phrase that represent the whole term. So for example, when we have the USA, which is an initialism for the United States of America, so the user can use USA or U.S.A with punctuation. So any form the user can use, the system must be able to return the documents that contain these forms. And after that, we use the MOBI thesaurus and linked it with the text search bundle. And after that, we use the word-to-vec algorithm, which is a deep learning algorithm or machine learning algorithm. This algorithm returns the set of words or the words that are similar to the search query based on its context. So for example, when you use a word-to-vec on any corpus, here we have some corpus. You have the table, the kitchen, the sink, the bathroom are similar words. Those are not synonyms to each other, but similar to each other based on context, when or where they appear. So we use the word-to-vec to return the similar word to improve the performance of the text search. And we were able, after that, to return the set of documents for any search query after applying the initialism and abbreviation, the synonyms from MOBI thesaurus, and after applying the word-to-vec algorithm. Any question? Mm-hmm.
What is the number of features that is returned by word-to-vec? So the vector has a feature length, right?
Yeah. So each vector is represented by 100 dimensions. Okay. Mm-hmm. Any other question? Okay, thank you.
All right. Thank you, Farah. Our next speakers will be Lili Shah and Gus Reyna. Lili is a PhD student also at Clemson. She's been an intern 3 times at LexisNexis. And she's recently started to work full-time while she finishes her PhD. Gus is director of at LexisNexis. He heads the engineering team for the motor vehicle Motor Vehicle Report Project.
Yes, sir.
Okay. And Gus has been with the company for about 10 years. So take it away.
Thank you. Is this on? Can you hear me? So thank you for coming. I got the delight to be able to present to you our solution today. I'm here with Lili as well. She's recently joined us, a PhD candidate from Clemson. And so today we're going to talk to you about the solution that the team put together to allow us to map public record data to standard categories. And there you go. So I'm going to talk about the background, the business problem that we had, how we approached it, and the solution. Then I'm going to talk about the approach for the system. If you're a machine learning practitioner, this should be a very basic review for you. But it'll give you a good sense for what we built to help us solve this problem. Lili will talk about some of the exploratory analysis that she did for us. She was an intern for us this summer and has done some great work, and we look forward to the additional work that she'll be doing for us. And then we'll talk about some of the next steps that we're going to take with this solution. So public records. Public records are data that's available. Most of our data comes from courts. And it's certificates for birth, marriages, it's licenses, professional licenses, foreclosures or tax liens. Right now, the data that we're working with has about north of 500 million records. And so each of these data events has a text description. And standards are great. Every state has their own. So if you're a business that wants to do business, who wants to run your business system across all 50 states, you need to deal with 50 different standards. So that's one thing that LexisNexis does well, and that is that we've mapped all these public record data events from different states into standard categories. That way a business can write their system to one standard and be able to process data across the nation. We have a team of subject matter experts that can map this public record data. So it's hundreds of millions of records. When you deduplicate or remove the duplicates on the text descriptions, it comes down to millions of records. And then those need to be mapped to about 500 categories or so, so hundreds of categories. So this team of subject matter experts, they are very experienced, and they know exactly when they see a text description which one of the 500 plus categories it needs to go to. However, people that don't have their experience takes a bit more time, and they may not get it correctly. And one of the challenges we have is that the data that was coming in was growing faster than our subject matter experts could map it. And that was delaying our data products' time to market. And as we know, time is money. So what did we do? Well, one approach is to grow the team, and we did that. But that's not without its challenges, because the trainers are the subject matter experts. And while they're training, they're not mapping. And it takes time. It takes time to go from a novice mapper to an effective mapper, to map all those records into standard categories. So we decided to use the HPCC systems after we did a prototype to do the classification and to assist these novice mappers as they travel down the learning curve of becoming effective mappers. The machine learning implementation would generate 3 recommended categories for each of these events. And this would shorten the time for team members to become effective. They could narrow down the hundreds to near where these 3 recommendations were made. And this also would reduce the time that the subject matter experts will need to train the new team members. This is an overall approach of how it works. Again, if you're familiar with this approach, it's pretty simple. These are actual text descriptions in our database. So you can imagine if you're a dog walking national business and you want to make sure that the person you hire is not one that has had a violation that says dogs running at large. These are the same 2 events with different descriptions because they were from different locations or different states. If you're an insurance company or you run some kind of a driving outfit nationally, that category 2 is probably something that you'd want to look into. And then we have this other category as well for if you're an outfitter, you want to make sure that your tour guides are compliant with the wildlife rules, right? That would be something that you'd want to consider. So this is the data that we start with. It's fully categorized by subject matter experts. The very first thing that we do after that is that we build our vocabulary. Lili will talk to you about some of the natural language processing tools that we have and that she uses to help us with the exploratory analysis. So the first thing is you have to clean and build your vocabulary. There's a stemmer, which again, Lili will talk about, that basically translates the words into uniform words. And so running becomes run, large becomes larg, and canine gets lopped off. And so the vocabulary is just the number of times that the word appears in all the records. So what gets passed to the model is just the counts. There's no meaning associated with what that goes, which having been my first machine learning experience, it kind of demystified it and was a bit disappointing to know that it's just numbers, but there you have it. And it works, so you can't argue with that. So you build your vocabulary, and then you have to split your data set into what the training data set and a validation data set. This is random distribution, 80 to 20%. This particular validation and training set split was pretty effective for purposes of this example. It is rarely, if ever, that clear, and there's a lot of work that you have to do with your data. So basically, then you have an 80-20 split between the training data and the validation data set. And so what happens here is that training data set gets run through the process that builds the models, and we use two model types, support vector machine and naive Bayes. Support vector machine is a curve-fitting multidimensional algorithm, and naive Bayes uses probability for its determinations. And so getting all those frequency counts and word IDs, we have the models. And then we'll take our validation data set. Again, we know what the category should be. And we run it through the model, and these are the top 3 recommendations. And dogs running at large, it's category 1, which is accurate. And it always happens like this, too, when we run it with real data, right? And then the other 2 category recommendations are it will give you recommendations related or not. It will give them to you. So we found out that our top recommendation seems to be, the support vector machine seems to be better at that. And so we use naive Bayes for the other 2. And so here you have new data that comes in. The training data is already in the model. You have cats running at large and handling without a license. So the models will then give you the top 3 recommendations. Those go to the mappers, and that feeds the whole mapping system. So that is at a high level what our approach is. So what were the outcomes? Well, that backlog of public records data that needed to be mapped went away, which is great because that meant that our time to market was not being delayed on account of data mapping. It had to be something else. And we were all much happier with the data mapping team, as were they, because now they could actually get to work on enhancing their data and not simply mapping all the time. We've actually found out that there are some text descriptions that are identical across different regions, and they have been categorized differently. So, and so now Lili will talk to you about some of the capabilities of the HPCC system.
Thank you, guys. Thank you for the awesome opportunity for me to finish my summer internship. So I have my poster here too.
Yeah, your microphone isn't on. Is it?
Can you hear me? No, not really. Okay, so I have to use this. Thank you for giving me the opportunity to do my summer projects, and I have a poster here too. So it is basically the same thing, using natural language processing technique to processing textual data. So from textual data, we definitely want to using natural language processing technique. And you may not, so is anyone here not heard this term before? No, perfect. So we have many common cases for using NLP technique. For example, we talk to our home device, our phone, and they're gonna give you an answer, and that's using NLP technique. And also for Google, you searching terms, and they give you back the documents, and you are translating your textual data. They all are using NLP. Oops. And also more, maybe a less common case is using NLP to sentiment analysis. For example, the Twitters. You want to see, okay, it's a happy Twitter or a bad Twitter. I love HPCC system, and NLP will tell me it's a positive, it's a happy tweet. So NLP is in our daily life, and it's commonly used for textual data processing. For my projects, I'm using NLP to process the textual data in MVR. So we have the idea using NLP, and the tool we are using is from our system. It's all built in. For example, fourth step, we are using tokenizer to tokenize the terms, the records into terms. So from here, one example is the operating VEH over max HJT, and we token them into 5 terms, operating VEH over max HJT. So after this, we're using the tokens filters using semantic analyzer to analyze the terms. For example, we return the unclear terms VEH to vehicle. So now we get the right form of the data. The next step, we are trying to eliminate human errors or some noise. For example, sometimes we have typo, like we change VEHICLE to VEHICL or just VEH. So we transform all these typos and mistakes into the most processed form, and that's a tool called Stammer. So Stammer will give us the processed terms to eliminate the noise, and this helps us do dimension reduction too. So we have less features, and they are more correct. The next step from Stammer, we go to the stop words remover. It's very easy to understand. For example, we have the, that, this. They are very meaningless for a human being to interpret the whole sense of the data. So we don't need to conclude them into our data. So we're using remover to remove the stop words, and then we have removed the over from the 5 terms and get the 4 terms as a final result. And then based on these results, we are modeling the terms into different n-grams. So n-gram means we are modeling the terms into different window or vector. So we ran different 1 gram, 2 gram, and 3 gram, and the results tell us the 2 gram is the most effective modeling for us. So from here, we're using 2 gram. You see our per vehicle, so it's 2 gram. It's come from the first 2 terms from stop words. It's out per vehicle, and from vehicle to max, the second 2 gram. So based on this language modeling, we get the final result is the 2 gram dictionary. With this dictionary, we can go to next step to put the results into our LDA model. So LDA is an unsupervised clustering program algorithm to clustering the documents into different topics. For example, I have thousands of documents, and they're about sports or cars or entertainments, and you don't need to use a human being to read thousands of documents. You're just running the documents into LDA, and it will tell you the topics is about sports, cars, and entertainment. So here's one example. We are putting the documents into LDA, and we can see here human beings have the knowledge about genetics, organism, species, extinct, and they are all belong to genetics and like extreme changes, climate, environmental, there means climate change. So with this human knowledge, we can see LDA run the same results as human understanding. The results is like 3 topics here. The climate change occupied the maximum portion of the topics. And then the second most important topic is genetics. So LDA almost copied the human brain to analyze the data of the documents. So using this powerful tool built in our ECL library, we analyze MVR. So the built-in LDA is a highly scalable LDA. It can massive processing big data in parallel manner, and also the hyperparameter setup. Oh no, I'm sorry.
Yeah, I can skip forward, sorry.
Yep, sorry about this. Yeah, so for LDA, we have many like hyperparameters, like alpha, beta. So they are the number to control how LDA runs on the documents. And for this, we can run like thousands of different sets of parameters into our scalable LDA parallelly. So that means we can run 100 different sets of input parameter like seamlessly at the same time. So based on this highly scalable LDA, we are able to running different number of topics on settings on our data. So our topic ranging from 10 topics to 1,000 topics. And our result shows LDA can tell us the basic idea of what's the topics inside our millions of MVR data. So for example here, topic 1, we have the top 5 terms is upper insurance requirements. So this is because they are not like wrong words. They are because they are stamped by the stemmer. So they are like this form. So the top 5 terms is operation, insurance requirements, proof requirement. So with the domain knowledge, we know it's more like a insurance proof related violation. Like topic 2 is unlaw speed, operation, unlaw speed. So with domain knowledge, we know it's most probably it's speeding tickets or something like that. So for maybe topic 10, we have 5 top terms is motorcycle, vehicle, unlaw, park. So with domain knowledge, we know it's most probably it's a motorcycle related unlaw parking violation. So all these are running by using LDA to analyze the millions of MVR data. So that is my projects using LDA to explore millions of MVR textual data. Thank you. That's it. So any questions?
Well, yeah, so our next steps.
Oh, yeah. I'm sorry.
That's all good. So we definitely are eager to continue the exploratory analysis that Lili's done. We also have some Roger Dev and Farah as well helping us with that. And so we're looking forward to how that will improve our machine learning implementation. The goal is to automatically map the data to categories, not just to make the recommendations. And we're quite a bit of far away from that. In the meantime, we need to keep digging, refining our existing models, and burn that dog is not running at large there digging, but we'll continue to dig with that as well. And last is to solve other business problems. HPCC Systems Machine Learning worked really well for us because it was the same language that all the developers used. The data is all in one place, and our developers are highly productive, so we were able to roll this out quickly, and it worked. Any questions? So the topic is an aggregate of all the text descriptions that she ran through the LDA. That's my understanding of it.
You said that there's 500 different, I guess, types of violations.
Standard categories, yeah.
Standard categories. Does each topic map to one of those 500 things, or not really? Or is that not the right way to read this?
So this actually we run on a sample. So I kind of summarize my projects, but the details there, the data is high skewed, so we cannot run one model in the whole data set. So we sample the data and run the model on the subsample. So this is the result of a subsample, so they don't have the whole set of the 500 different categories.
Yeah, so these were the topics that were identified in an unsupervised manner based on looking at the data. And so this is part of a number of algorithms as well with Roger that we're going to look at and see how they can apply to our current modeling.
What do you use the topics for?
So actually, in my poster too, I have some explanation. So based on this, actually FDA can perform as a dimension reduction tool. We can feed the results into the next stage, downstream into different classifiers to classify the documents into different categories. So next step, we can do improve the results, maybe not using LDA or different kinds of machine learning techniques, and build a data pipeline to do classification.
Are you planning on having some sort of human readable description of each one of these topics? Something that you could, once you've classified, you could show the person, in regular English instead of this one here.
Yeah, we can do that. There's some research about how to interpret the topics of LDA. Yeah, we can do that, but right now we don't have those plans to translate topics into.
And if you think about this feeding upstream the other models, it doesn't require it to be human readable, right? If you want to have the same tokenized STEM words to pass along, assuming that we'll put this upstream from our current models.
Okay, we have time for one more question. Anybody? Okay. Well, I want to thank you, Gus and Lili and Farah, and thank you for coming. And I want to thank the live stream audience. We are going to take a 10-minute break, and we'll return for the next session after that. What's that? They told me there was one. I don't see one. That's curious. and welcome to the live stream audience. We're going to start with a presentation by Shah Mohammed Hamdi. Hamdi is a PhD student at Georgia State, and he worked with me as an intern over the summer, and he's going to do a poster presentation, and then we'll get to our main speaker. Hamdi?
Hi everyone, and thanks Roger for introducing me. And I'm doing a PhD in Georgia State University in the focus on data mining and machine learning. My lab's name is DM Lab, Data Mining Lab, and my advisor's name is Dr. Rafal Angrick. And in this summer, I worked with Roger Dev on the topic of dimensionality reduction using Pbblas. Pbblas is a library for handling matrix operations in HPCC systems in a parallelized manner, and we needed dimensionality reduction algorithms to be implemented in Pbblas. So in the Pbblas, the matrices are stored in a format called layout cell, okay, which has 4 fields: work item ID, row index, column index, and the value. Okay, so we had to convert our data matrices into the layout cell format and then apply the PCA and kernel PCA algorithm. So at the first of the internship, we worked on the linear principal component analysis, and which is just the singular value decomposition of the covariance matrix. So there are several types of matrix decomposition algorithms like LU factorization, Cholesky factorization, singular value decomposition, eigen decomposition, etc. And in the Pbblas, LU factorization and Cholesky factorization was already implemented, and we had to implement singular value decomposition and eigen decomposition and keyword decomposition for our purpose. And at first, we worked with the toy MATLAB datasets, which had 50 samples and which were 2-dimensional. We tried to validate our results using the MATLAB's PCA implementation as the baseline. And later, at first we worked with the Cholesky decomposition-based solutions, but later we found that the results that is found after Cholesky decomposition is not exactly matched with the MATLAB baselines. That's why we went to the classical approach of SVD-based approach. And later, we also moved on to the nonlinear dimensionality reduction, which is kernel PCA. And we implemented 3 types of kernel for this algorithm. And kernel is just a similarity matrix between each pair of the data points. And we have implemented linear kernel, Gaussian kernel, and polynomial kernel. And when we have the kernel matrix, we normalized those matrices. And finally, we did the eigen decomposition, which we developed in the first part of our project. Okay, and when we have the eigen decomposed matrix, then we can just fetch top k columns or top k eigenvectors, and those top k eigenvectors work as the reduced representations of our data point. And that's how we reduce the dimensionality of the data. And we have also worked with some other datasets too, like Friedman forest dataset, which had 4 columns and I think 1,000 samples on it. And finally, we committed and pushed our code in the dimension reduction repository of the HPCC systems. So you can see the code in that repository. And finally, we also increased some more machine learning capabilities of the Pbblas library. For example, right now, Pbblas has more functions for handling vector operations. Like you can construct any vector with a given length and constant values. And you can also make a vector or a matrix of only ones, only zeros. You can make the identity matrices. Actually, these functions are trivial, but they're used very frequently in other machine learning platforms like MATLAB and scikit-learn of Python. So right now, actually, even Pbblas have those kinds of functions. Also, we have the norm calculating functions, L2 norm and Frobenius norm for matrices. So right now, after this project, actually, we have increased the machine learning capabilities of Pbblas. And that's it for now. And in the future, actually, we also think to work on the feature selection algorithms like Fisher and MRMR and Laplacian score for using in the ECL-ML repository. And that's it from me. So thank you very much.
Thank you, Hamdi. Now I'd like to introduce Mr. Itauma, who's a doctoral candidate at Keiser University. He's also has been a computer science instructor at Wayne State University and is currently a lecturer at Southern New Hampshire University. And he has a very interesting talk.
Hello. Good afternoon, everyone. So today I'm going to present a topic that is related to my dissertation. Yesterday I did present a poster on cervical cancer risk factors exploring analysis using HPCC systems. However, my presentation today is in the aspect of education. I have a famous quote that says that education is the greatest weapon which we can use to make the world a better place. And first, I'll start by introducing myself. I am a person, people say I'm a jack of all trades, and I try to be a master of all. I have 2 masters, one in computer engineering, the other in computer science, and I'm currently doing a PhD in instructional design and technology at Keiser University. So my goal, it's all about how do I improve students' success? How do I improve students' performance in education? Okay. All right. But before I get into the goal, the first, what motivated me into education? So the first thing that motivated me is the fact that I have, in my years of being a teaching assistant at Wayne State University and also an adjunct professor at Wayne State, I have always noticed that in my classroom, they have always been predominantly male students in the class. I teach the lower level undergraduate students programs. And so for my doctoral dissertation, I thought that it would be nice for me to examine why do we have this situation? Why do we have very low female enrollments? And also, there are also other factors which I had suggested would also play in this project. I was so happy when I saw a project presented by the high school students on autonomous agricultural robots, and I thought that this is very innovative because it's this kind of projects that would motivate the high school students to enroll in STEM programs. And I will move forward. So now, the outline for this, in this presentation, the topic states predicting STEM enrollment. However, I will be talking about the different associations of different variables which I propose are important in determining if a student would have an interest to enroll in STEM or not. And this is not all the variables that are in the data set, but just for the purpose of the presentation, I selected 3 main variables. So Science, technology, and mathematics is a very important skill in today's world, and it's important. And today we have a very large growing workforce in the field of science, technology, engineering, and mathematics. And one of the reasons why this skill is important is because it helps students to improve critical thinking, to improve their analytical skills, and these skills can cut across various educational curriculum. So it's important that that STEM projects are introduced at the high school level. So the major background of this study is that the supply of STEM workforce needs to keep up with the demand today. And for this study, I would be examining the high school longitudinal national cohort study of 2009. And so these are the three variables that I would be examining in the study: science self-efficacy, science identity, and science utility. Now, science self-efficacy means a student has confidence about the ability to succeed in science. Science identity is the student sees himself as a science person, and science utility is the perception a student has in regards to STEM activities in the community or in daily lives, etc. Now, there are more. This is called out of the survey that was conducted. And these are basically constructs from the data sets. And I wouldn't say that all these three variables are exhaustive in predicting STEM enrollment. However, just to play around with when you're starting the research, the first thing you do is an exploratory analysis. And so this presentation is more on an exploratory data analysis. Okay, so my objective is to determine if high school students' perception of science, self-efficacy, identity, and utility are associated with their consideration to enroll in STEM. Now, my intuition here is that a student who sees himself as a science person and also sees himself, understands the essence of science in the community, should naturally want to enroll in STEM. And a student who is confident about STEM programs should also naturally want to enroll in STEM. Now, apart from these variables, we also have math self-efficacy, math identity, and math utility. However, for this presentation, I'll only be showing the association between these three variables. And my prediction is that when we look at the association, we might be able to come up with interesting insights by comparing those associations based on students' consideration to enroll in STEM. So, like I said, the data set utilized in this study is the high school longitudinal study, cohort study data set of 2009. It was from the ninth graders of 2009. And this is still an ongoing study. So longitudinal means that they have they are following up the students over the period of years. And so the data set is of over 23,000 ninth graders from 944 schools. And so a bivariate analysis was conducted for this study. Now, looking at the correlations between science, self-efficacy, identity, and utility, you could see that the correlations are not really, did not really have a very strong correlation. But now the beauty of seeing through data is it's not enough to just look at the descriptive statistics of your data, but you should also visualize your data to gain more insight. So even though your data, two variables might be strongly correlated does not really mean that they are, that one could be the cause of the other. And there's a famous saying that correlation does not really imply causation. And so now, so here's a visualization of the two variables. Now, this really looks so scattered, but then if you look into this visualization, there are things that we can come up with. Let's see, does this work here? So for me, I'm more interested as an educator with the people at this point and at this point. Now, because looking at the scale, the higher the science utility, the higher the science efficacy. I would expect that, so the orange line, the orange circle implies students that enrolled in, that has a consideration to enroll in STEM, and the blue color is for students who do not want to enroll in STEM. So I would wonder why a student who has a very high science utility and very high science self-efficacy do not want to enroll in STEM. And of course, this would be natural. A student that has a very low science utility and science efficacy would naturally not enroll in STEM, but I would have expected to have more orange points, data points at the upper right corner. And so I did the same for science identity and science efficacy, just to explore the data to see if I can draw some insight from this. And also did the same for utility. And I could see a common pattern between all the data. And of course, if you have any questions to ask, I'm happy to answer. And if you would like to know why I'm utilizing Tableau instead of the visualization bundle of HPCC, I could also answer those questions. And so now, I also, just for the sake of checking up, using performing to see if science utility explains science efficacy, I did try to do a simple linear regression on the two variables, just to see if there's anything statistically significant. But the purpose of this is really not to see if there is any statistical significance between the variables. The purpose is just to visualize the relationships between the two components and to see if it proves my intuition regarding one who has confidence in STEM, one who sees himself as a STEM person, and one who understands the importance of STEM in the environment, basically. All right, so are there any questions so far? Okay, so why am I using HPCC? The goal of this is just the preliminary of my dissertation in which I would be exploring this data set to come up with interesting insights, and I would be utilizing various regressional models to explore the relationships between the various independent variables that exist in the data set with the dependent variable, which is the consideration to enroll in STEM. So that is a future work to be done towards the completion of my dissertation. And the other reason why I'm using the platform is that HPCC Systems is that it has a very strong machine learning library, which I could use to gain more insights in examining this problem. So now, earlier this year, I did give a presentation on exploratory data analysis using the visualization bundle of HPCC Systems, and I must say that it's an excellent tool for data visualization. Now, the reason why I used Tableau is because earlier in the year also there was a download in which they talked about a web connector between HPCC Systems and Tableau, and I thought I'd just give it a try to see if I could just use it for visualizing data. And currently at Southern New Hampshire, I teach a class in data visualization. And in trying to introduce my students to HPCC systems, I see the need to tell them that you can all have your data spread to one particular location to HPCC systems, and then connect your data to Tableau just for visualization, because in the school curriculum, Tableau is being utilized. Other than that, everything that I did in Tableau, you could do with the visualization bundle of HPC systems. And so that is how you make the web connection with HPC systems to visualize your data. So basically, if you have your data, you can store it in one location, and you can always exploit in Tableau. Or moving forward in my dissertation, I would not have to utilize Tableau, because you can't use Tableau for, you can only use Tableau for simple linear regression, but for multiple linear regression, you can't really use Tableau, and that wouldn't really solve what I'm trying to solve. So basically, moving forward, I'll strictly be using the visualization bundle of HPC systems and the tools that Roger Dev has talked about. I did also play around with the learning trees that was discussed, and of course I got results that I didn't feel so happy about yet, because it's like it's said that regression is more of an art and not a science. So a lot of I will still need to put in more time to play around with different variables, and not just with the learning trees alone, looking at the logistic regression library of HPC systems, and at the end of, and hopefully come up with interesting insight after conducting these experiments. So, in conclusion, so positive correlations regarding consideration to enroll in STEM was observed, and the result shows some interesting clusters that educators can need to investigate moving forward. Thank you.
Thank you, Itauma. And this concludes this session of the HPCC Community Day. Thank you, everyone, for attending, and thank you to the live stream audience.